Hi everyone, this is Miriam Naime from Newcastle University and the Alan Turing Institute. Welcome to our SuperGen Smart Charging webinar series. The webinar is an activity of the Vehicle Grid Integration Group at the Alan Turing. The Turing is the National Institute in the UK for Data Science and Artificial Intelligence. And one of the objectives of the Institute is to apply data science methods to help solve real-world problems, such as what we are doing at the Vehicle Grid Integration Group, where we are developing tools to help decarbonize transport and electricity infrastructure. We have a YouTube playlist for previous talks we hosted on the webinar. These include talks on communication protocols for electric vehicles, such as ISO 15118, OCPP, and other communication protocols that can also be applied to electric vehicles. And to name a few, OpenADR, EEBus, KNX. We also hosted talks on cybersecurity, such as how we can deploy a public key infrastructure to secure and authenticate messages and entities involved in the EV charging infrastructure. Finally, we also had talks on regional and national plans for the rollout of electric vehicle infrastructure, such as the talk we had by Peter Bach-Andersen from DTU. And today I'm delighted to host another speaker from DTU, Thomas Meier. Our colleagues in DTU have been involved for over a decade on projects on electric vehicles. They have asked and answered really important questions and always shared information that helped other projects build on our findings. At least this is our case. Thomas today will discuss what is needed for an electric vehicle to act as distributed energy resources. So for example, what are the informational and control objects needed? And Thomas will mention as well some of the enabling standards. Thomas has been involved in several European and national projects, to name a few, Parker, Kotevos, ACES. And he's been involved in international EV standardization efforts. So without further ado, Thomas, over to you.
There we are. Now I got the control.
Yeah.
Well, first of all, Miriam, thank you for the introduction, and also thank you for this very nice series of webinars. And I can highly recommend them to anybody who would like to know a little bit more about the subject. But regarding my presentation, let me just start. This you all know, this was from the invitation. So I'm going to talk a little bit about what would make an EV an ideal part of an energy system, basically a DER, distributed energy resource. There we go. So my biography basically is just in the presentation, so you can look for yourself. The agenda that Miriam just introduced, so I will have the floor until 12:50. So basically, I hope we will enjoy the next 45 minutes together. The vision I'm going to present you today is basically that you should be able to connect any EV to any kind of EVSE or charging station, and then it should be able to perform a service for any given service provider. This really means that the EV should be able to plug and play, just connect to a charging post, and then anybody, the grid or service provider, should be able to utilize it as part of the grid. That's our vision. That's what we've been trying to do for quite a few years, but there's still some issues, and I'll get back to those. So a little bit about DTU. Basically, the reason why DTU, more precisely DTU Electro, is interested in EVs is not really the car themselves. It's basically the energy system. In DK, we have a very high share of renewables, primarily wind turbines and sun. The problem with these renewables is that they lack inertia. Here we're looking into using inverter-based inertia, and then EVs is part of the solution. We also look into a lot of different solutions, but EV is one of the bigger ones because basically the battery contains a lot of energy, but heat pumps, any kind of pumps, is also a major part of this system. We have a group primarily based around DERs and research group leader Christian Traholt. So this is a small advertising. If anybody wants to work with us, you should look Christian up. So back to the problem. If anybody has heard a talk from DTU, you probably have seen this slide before. It's basically a show of wind production. It's over 21 days. And then if we see the sort of the demand from the grid side, then you can see the problem. We have periods where we have too little energy, basically when the wind is not blowing. We have periods where we have too much wind, when we have too much energy in the system. And we have periods where it fluctuates, where it changes. All of these problems can be remedied by means like an EV and basically other parts of DERs. This is only on sort of the energy side. You could make the same graph using something like frequency and then stabilize the frequency in the grid. You could use it on harmonics or general THDs. So this is just a simple example, but basically the EV is extremely good at covering some of these situations. So if we look at like the old world, we would have a very strong generating system. That would be a very high degree of inertia, some rotating machines based on nuclear power, any kind of fossil fuel. This would make for a very stiff, a very robust system. Now we're moving into, we have a lot of different, I can see the sound might be unclear. Is that a general problem?
Thomas, it is okay generally, but if it's easier for you to change microphone, there's a bit of echo, but in general it is okay.
Let me just see. I'll change, then I'll swap to the PC, then I'll just need to talk into the screen, but okay, I'll do that. No problem. Generally saying, then we had a very robust system, a large generation. Now we're looking into like the new world, where we have a lot of different kind of energy producers and energy consumers. This is what we generally address as smart grid, if it's controllable. There, electric vehicles is sort of like part of the solution. Just a little story here from Denmark. I mean, several weeks a year, we will shut off all the fossil fuels-based generation. Basically, we're going to not just 100, but close to 150% renewable. And this is doable due to very solid forecasting, etc. But of course, the aim is to go to 100% renewable all around the year. We're not there yet, but basically we are improving our sort of effort in this area. So it should be done by something between 2030 and 2050. We should be at 100%. Well, back to the subject. We'll just see if we can use EV as a DER. One little item, be aware that we're looking into not just the electrical system. We're looking into a sector coupling of all the different kind of power system, gas systems, district heating, etc. Here we have obviously the wind and the sun going in. We have from the transport sector something going out. And there, as this talk is all about, an EV can be used as a DER. But it can also be used for little grids like nanogrids, which is basically just your own house, microgrids, which is like your neighborhood or just surrounding buildings. Common for all of this is that you really need to control the EV as what I call a DER. So let's look into what this control should be about. This is the basic setup. Again, this is a drawing I nicked from the Parker project, so quite a few of you have probably seen it before. It's basically how you have some sort of control here called the aggregator. It could be a service provider taking control. In this picture, I'm showing the control going into the charging station. This could go into the cable. It could go into the EV. It could even be done directly in either the charging station, the cable, or the EV in some kind of autonomous way. We've done this, and it can be done, and I'll end all this presentation with a little example of how it's done. But for now, this talk will go on this simple setup where we have one aggregator controlling the charging station based on information from the grid. All of this was really started not by us, but by Willie Kempton from the University of Delaware, who really got the title, the father of vehicle to grid, because he basically started this when he realized that having a lot of wind turbines, we would need some kind of storage in the grid. So Willett talked about V1G, which is basically control charging, but also V2G, or vehicle to grid, and in that way sort of making the EV a part of the energy system. This was really done also before 2009, but there he got an e-box, a little specially designed car. They only made like 25 of them. We got one here at DTU as well. And that was really where we started our adventure here at DTU. Since then, we made quite a few more projects. Let's look into that. What you see now is how we, from 2008 and forward on, have sort of done a lot of different items. The Edison project was really theoretical, really looking into sort of what can be done on the island of Bornholm. It was a rather large project. All of these projects is around roughly between 1 to 15 million euros. So you're looking at, again, roughly 100 million euros on the screen in total project funds. But the Edison made a very nice theoretical work, a little bit of practical work, but that's basically what we sort of like have been building onto ever since. The little project you see on top, the Nevic, was a test center. But basically, look to the right where we're going to the Nikola and the Parker project. That was based by work on Peter Bach-Andersen and quite a few more. And that's where we really looked into making this EV integrated part of the electrical system. To get there, we basically defined this VGI, or vehicle grid interface integration. We also looked into more the grid side, and that's the bottom part of the project, because there we're talking about heat pumps, we're talking about inverter-based system, we're talking about grid-connected batteries. In the iPower project, it was also a very theoretical project. We basically made a marketplace where you could sell whatever kind of service you have. You could sell the flexibility. In the case of the EV, it would be the battery capacity. It could also be frequency control or harmonic compensation. These two items are really what we combine together to sort of continue working. And the issues come when you sort of look into some of the standards involved in this grid. Back in the Edison, we looked into 61850, which is like substation automation. It can also be used for charging an EV, but it's a quite heavy standard. We looked into the 62196, which is basically plugs for EVs, so interoperability, making sure that any EV could charge at any charging post. And then the 61851, which is really into how does the car charge. We looked into the control, the PWM signal, which is what we use to actually control the charging. But we have quite a few more standards. The Open Charger line has OCPP, etc. We looked into 15118, all of this in the Kosovo's project. We continued, and this is pretty much the ongoing project, with implementing them. And the 63110 is basically a joint venture of OCPP, 15118, 61850, etc. It's sort of like trying to get the OCA standards into the IEC framework. On the bottom part, you can see that we're still working directly with the OCP standards. Basically, this is what we used to do vehicle to grid on and the new chargers. We did vehicle to grid in the Parker ACES Nikola project using the CHAdeMO standard. And we're going to use the OCPP and Combo to do vehicle to grid in the TopCharge project. I'll not talk a lot more about this project. Basically, I could talk around this full 45 minutes on either of these projects, but I'll try to just take very, very few examples that sort of tells the story I want to tell. So, starting with the project, the Parker project. This was made with quite a few partners. This was made in the lab, but very importantly also in real life. And this is where we came up really with this definition of VGI, that the car connected to the grid should be able to either sort of benefit your very local surroundings, your own building in a nanogrid, there's sort of like the neighborhood, could be a microgrid, or even the full grid, sort of a regional status. And if you look into the Parker project, you'll see we tried quite vast amount of different services. And that worked out fine. One of the things we discovered, one of the things we tried, was that since 2016, we've had 10 cars connected at Frederiksberg Forsyning, rendering services to the grid. And they are doing this on a fully commercial scale. They're still doing it. There are more cars connected on Bornholm, all controlled by the aggregator Nuve. And this seems to be working super fine. Now, there were a few issues in the standards, and there were a few issues that made this not work perfectly as a fully ideal DER. Some of the issues we'll look at here on the next slide, which is basically the general setup where we go from right on the EV to the charger, electric vehicle supply, the equipment to the charge point operator, the aggregator, and the grid operator. All of these entities need to talk together somehow. And from left, it could be using some of the OCA standards. It could be using OpenADR, as some other people have been giving very nice talks about. It could also be using between the charge point operator and EVSE, some OCPP, etc. But basically, what we did in the Parker project was that we cheated a little bit. And you can see there's a small box called the VSL, the Vehicle Secure Link. That was developed by Willie Kempton and the Delaware University and implemented by Nuve. And basically, we got some of the information we needed. This enabled this control of P and Q. We needed some observability state of charge. We developed a CAN bus reader that could deliver that one. And also, we had some issues regarding target values, and where we developed what we call the Parker test. I'll not come into that, but basically it shows that an EV can render service to the grid. So the cheats were the VSL, basically enabling the charger and the aggregator to talk together. We manually put in the battery capacity of the cars because that was not communicated using the available standards. And we also had some issues with the ID. We do not know what car drives to what charging post. So basically it works by having the same car drive up to the same charging post every time. And that's not really ideal. It's not really plug and play, but it works. So,
Thomas, apologies to interrupt you.
Sure.
There is a bit of issue with the sound. Are you maybe able to move the microphone a bit away from you, or is there any other way that you use something else?
Let me try to move away from the screen. Does that help?
This does not help, no.
Let me try to swap. I do have different microphones.
And I can edit this later on. But
Now I swap to the webcam's microphone. Is that better?
I think that's better.
Okay. I'll continue with this then.
Thank you, and apologies for interrupting.
No problem. So basically, we are into some of these requirements, the definitions of what we would like to have in order to call an EV controllable and a perfect DER. Basically, it needs to be controllable. This is what we see when we're doing V1G and V2G. We can control the charging. It's a set point. We prefer it per second, but basically that works. We would like some measurability, both on the grid side and the EV side. This is needed in order to make sure that the EV is actually doing what it should do up against both the grid and front EV. Then we need some flexibility. That's basically the the energy amount you have in the battery. And that's not the full battery capacity. For instance, a Leaf would accept to be controlled between 20 to 80% during vehicle to grid, and that varies from car to car. So we need a definition so that the grid will know how much energy can be moved around. We need it to be traceable, pretty much who controls what. This I'll come back to because that's all about the standards. And then finally, but not least, we need some kind of cybersecurity. It needs to be undisputed who is controlling what when. This does not mean that the user cannot use his car, etc. It just means that he has to put in his preferences as to how the car can be used, and then the service provider can use that interval to actually control the car. So the V1G, the V2G, now we need to get control by. There we go. So all of this combined would be what we call vehicle grid integration. And if all of this is solved, we would consider the EV to be a DER, distributed energy resource. So next, I'll look into this traceability, and that's basically into the standards. Before, sorry, we just have a little example. This is direct data from the island of Bornholm. You can see in the green slide, that's the wind generation. The yellow one is the solar generation. And then the purple one is biomass. You can see they have very different patterns. What you then see on the last one, which is blue and red, is the interconnection from the island of Bornholm to Sweden, where they're connected to the energy system. And that's really sort of like the imbalances of the system. This can be remedied by different means. You can start off different kind of generators. You can have energy storage, or you can, as we've done with success now a couple of years, use an EV either using vehicle to grid, which is clearly preferred, or just use a control charger, which is the small one you see on the right. This we are now scaling up, so we are not just using 1 or 10. Now we're trying to go to 100 or even 1,000 if we get enough EVs on the island. And basically that should make the island of Bornholm quite more stable. So it's not just for fun that we're using these EVs, and it does work in real life scenarios. So the standards. We do have some problems, and we call them informational objects, and they need to flow around across the standards. Sometimes they're not enough. That could be like the ID, the state of charge capacity. We have some control objects. That would be a set point of different times, either PQ or different harmonics. And then it's not always that the ID is being transferred. This old picture back from 2013 shows some of the standards. Here we see some of the issues. If you're using the 61851, you do not have really direct control of the charging. You're controlling the limit. You cannot control it below 6 amps, and basically it goes to 0. You do not really have the state of charge of the battery capacity, and you do not have the ID of the car. And that's some of the issues that we addressed in the Parker project and sort of worked around. If you go to the 15.11.8, which is being remedied in many of these, then the first version did not have vehicle to grid. It did not really have plug and charge. So there were some issues around this. Let me be quite frank, we have not dealt a lot with this since 2019. It's basically where Corona said a little bit of stop for that. But I've asked the guys in some of the joint committee regarding the work of it. It seems to be on track, and we will look into it in our top charge project. So there's OCA, which this is no offense to OCA, but it's not a real standard when you ask IEC. And there's no real interface to IEC standards unless you consider the new one, the 63110, which is really a test of trying to implement it into the IEC family. And now comes the IEC 63110. And now I'm saying has no grid data. That's not really correct. It would be more correct to say the grid data could be better. We'll look into that. I've got a simple slide on the latest information on that one. Now, we've so far only been talking about e-mobility. There we have some reference architecture. This looks a little bit complex, but we actually have the same on the smart grid. And they have the same issues regarding being a DER on either side. So we're really trying to get these two parts talking together, and that's sort of a joint work in IEC. There are different joint task force, etc. But really, these two sides should be able to talk the same language. We're talking about object models, we're talking about informational models, and objects. All of these should sort of flow in the same way, all the way from the EV and up to the market. So basically all around these two pictures. And there we come back to these 5 items. If this is on either side, in either standard available, then you really have a lot more interoperability, and you can consider any given object, battery capacity, etc., a DER seen from the grid. This is a little bit about the standards. This is a little bit about where they sort of are. As you can see in the dates, it's from 2019. But I asked my friend from the standard, Klaus Andersen, who was on this slide, what the status was, and he said, well, due to Corona, it's not really a lot different. I know there's a lot of work going on. I know there's a lot of testing activities and joint clock parties, etc., where you can test your equipment, but let's see what actually happens. As I said before, the 63110 was really a try to sort of merge both OCPP, which has some kind of object model, and then 61850, which has a different kind of object model, and trying sort of to merge them together and then making sort of it work more interoperable. So basically you would say it's a test of, or try to get OCPP into the IEC family. It seems to be that it's kind of taking its own life, and the 63110 is really getting quite complex. What we're seeing is that they'll have models for DERs. This is very interesting. This could be some of the issues I've been asking for, and we will definitely test them. Remember, whatever I've been telling you now has been based on testing, has been based on demonstrational projects. So what we see now is that we are really describing DER from electrical and functional characteristics. We'll have some operation nameplate, etc. We're also going to see that some of the identifier will be put in, something we've been lacking. There'll be a lot about sort of like the market, and that means we're going further up in this, this overview. So basically people can ask for some kind of a service, and then the EV or any kind of DR can provide it. This is one of the issues that really is difficult in demonstrational project, to really show this not just in the lab, but actually in real life. So as you can see in the bottom part, we are definitely going to see something like set points. This is also a part we've been asking for, so I'm quite happy. So let's see what actually happens in the future. This is an implementation where we are sort of going to see. It's an ongoing work. It's a quite heavy work, so it will definitely take some time. Now, back in 2013, we ended Cortevas. We ended with the reference architecture, as you can see here. This has not changed a lot. It's basically just different names, etc. At that time, it was the same goal. We should have informational objects. We should have them flow all the way from the bottom, where you have the electric vehicle, all the way up to the top, where you would have clearinghouse, energy markets, etc. So it's not that sort of like a lot has happened in the last 8 years. It's more a question of the standards being developed. It's a question of use cases being brought to the standardization committee. So like from demonstrational objects, from demonstration projects. So sort of like we're looking into a situation where the standards are slowly, but rather steadily maturing and making a lot of this possible. So to slowly wrap up, and I do know I'm a little bit fast on this, but I think that was what happened. What my vision is, what the vision is that we are addressing here at DTU is that any EV, again, can charge on any kind of charging supply equipment, and it should be capable of performing services from any given service provider. Then it can be considered a true DER. Just to spin a little tail on this on service providers, this can be people who want to do frequency regulation. We are seeing private companies doing apps, doing equipment that can actually do this here in Denmark. It could also be that the grid, that could be the TSO or the DSO, has some kind of service they would like, then they would go into the role of a service provider. This could be service as frequency regulation, but also something new, something like harmonic compensation, something like reactive compensation. And all of these items are like the grid side would definitely like to have them. The EV is actually quite capable of rendering these services, but so far the two sides has not really met. And some people would say you need the market to drive this. But let's be quite frank, there's not a lot of money in some of these services. So there's not been enough pull from the market to actually drive it. So my take on this would be that we'll show it on university level. We'll show that it can be done. And then hopefully it'll either be done mandatory. We do know that from the UK, something like that, if you have flexibility, you should make it available. Or it could be that some of the market requirements, some of the frame conditions are being changed. Basically that there's more money into these ancillary services. And then perhaps we could see that quite a few more of these services become available. And then it would make it quite economical, attractive to put your car available to the market. I didn't mention it when we saw the Frederiksberg, but for the last couple of years, we've been gaining what's roughly 1,000 Danish kroner per month per car. And that's sort of like payment from the market for the service. It does not really cover energy expenses, but still it's a pretty decent revenue. And that would mean roughly 100 and 120 euros per month. But with that, I would actually end off a little bit fast. Sorry for that, but that happens. So basically, any questions?
Great, thank you, Thomas. Yes, plenty of questions. Maybe we can start with the slide you had on distributed energy resources and maybe the different, yes, this one.
Sorry, got a little bit too fast. Which one, sorry?
This one. So where is this coming from?
This is from the, well, I'll just go one slide up. This is from this IEC, the Joint Work Group 11. So that's basically a work group under the Technical Committee 69 and 57, so smart grid and e-mobility. And they are trying to get this standard up and running, a little bit like I showed you a few slides before. So the joint work group from IEC.
And do you foresee this standard to be, so when you say generic DER, so what if we want to control not just the electric vehicles, but obviously other distributed energy resources in the house, for example? How does that apply to other things? And are there already some protocols that can do that are generic protocols?
I mean, there are protocols, and that basically just takes a lot of work to get them going. I mean, you mentioned KNX, that can be inside. We're talking about different kind of home automation systems that can be controlled. But in my opinion, what's very common for all of these is it takes a lot of work to make a simple setup work. It's nothing like plug and play, you just add extra items. You can make this work, but you need to put in quite a few hours before it's really a part of the energy system.
Do you foresee a future where a charging station is talking two different protocols? Maybe one is specific to electric vehicles like OCPP or IEC 63110, and another one is a protocol that could communicate with an EMS?
I would say put it a little bit different. I would strongly recommend that it could. I think it has huge benefits if it's a kind of plug and play device, and then it's up to either the user the installer or the site owner to decide how the equipment should be used. So definitely, yes, more interfaces, more standards that could be addressed.
Okay, to ensure interoperability and maybe having OCPP or IEC 63110, we don't lose the transactional aspects from what these tools could provide, and something like, let's say, for example, EE-bus would allow us to manage an electric vehicle charging station as part of the house.
Definitely, yes.
Another question I wanted to ask is about the approaches. So right now it is mostly controlling the charging through the EVSE, through the charging station. There are some examples of projects where the charging is controlled directly with the car. Can you comment a bit on this, maybe some disadvantages of this approach, or can you see it becoming more prevalent in the future?
This depends a lot on the car producer, the OEMs, because basically, I'm just talking about our experience. Then we've been using some kind of API, apps, etc., to control the car, and it's either slow or not really controllable. Having said this, if the car producer would sort of go into this and sort of make it possible, then it's clearly a preferred way, because then you would use the car's BMS, the battery management system, and then you would actually directly control the charging. The way we're doing it right now using the PWM signal is really not controlling the charging, we are controlling the limit. So yes, I do believe it's a good place to go into directly to the car, yes.
And if we do go directly into the car, how are we able to take into account what's happening on the network?
Then you need the measurements from the grid to go in, and then you would still need some of all of these standards that we are talking about, unless that you actually measure this in the car. We've been doing this where we pretty much we've been building EVs, etc., where we built some, for instance, frequency meter into the EV, and then the EV was actually on an autonomous basis doing frequency regulations, and this can be done.
Okay. So my understanding, maybe to summarize for myself, is no matter what approach we use, either we go through the EVSE or we go through the OEM to control the car, there are certain informational and control objects that we need to ensure a seamless and proper integration of those vehicles into the grid.
That is absolutely correct. And that's primarily battery size and sort of like energy size you want to move.
Okay, so taking the point of battery size, energy size, as far as I'm aware right now, we cannot get the state of charge through the ISO 15118. Is it absolutely necessary to get this information, or is there an alternative way to get some sort of other information to be able to let us do energy management while respecting the energy available on the battery?
I mean, there are alternatives, but they're not very good. So in my head, yes, it's absolutely essential to get the state of charge. First, the battery capacity, then sort of the available battery capacity, sort of the flexibility available. And then finally, the state of charge, so sort of saying, where are you? Are you fully discharged, fully charged up? I think that is essential.
And if we are not able to get that, do you have any, you touch on it during the presentation, are we going to get this information from ISO 15118? I'm aware that we can get that from CHAdeMO, for example.
That is absolutely correct. I think yes.
But if we don't get it from ISO 15118, how do we go about it?
Well, you can cheat a little bit like we did. We got it from the CAN bus. You can do it manually, basically, like we did in the Parker project, and sort of put it into the system. But then you're very then you need to be very sure that it's the correct car that's running up there. To be quite honest, I can't really see a way around not having the state of charge. So we would have to find it somehow.
Okay. All right. So we talked about OEM versus EVSE control approach. There are other things. There are another area where we do things right now in one way, but it doesn't need to be that way, which is the AC versus the DC approach. Right now, specifically V2G, most of V2G trials are done DC way? Do you see a future where we see a mix? Are you able to comment a bit on the cons and pros of each approach?
This becomes a little bit like what are your preferences? It's nearly a religion to talk about whether you're doing vehicle to grid on board or off board. My take on it would be that if you do it like we're doing it right now, only DC wise, then it would make the car a lot simpler. You would not need this bidirectional charger on board. Then all of sort of the advanced stuff would be in the charging station, the charging post. I can see the other way around where people argue that if you put it on board, then the charging post would pretty much just be an outlet. But still, in my head, it makes it a lot more sense to have the expensive equipment in the charging station and then having the car as simple as possible. And that means actually that it would only be DC chargeable. That means that I would pretty much take out the AC charger of the car and then only have it DC charged.
Okay. And anyway, in DTU, you did investigate more than one approach. I think I remember Martinenas, I'm hoping I'm pronouncing his name correctly, in his thesis talked about something integrated charger, inverter, motor control inside the car. But okay, as you say, there will be pros and cons of each approach, and maybe more work is needed to properly assess each way.
That is correct. You can see integration. I mean, you've also seen it from the Renault Zoe. You've seen how they can sort of integrate, make an extremely flexible charging device, which can make it AC chargeable around a very vast area. I think it's from a few kilowatts up to a 40 kilowatt area it will have. This is interesting, especially if you're making it bidirectional. And there you can see there's a demonstration project right now with them. But I think, and that's only a personal opinion, I think you will see that the cost on the car will be too high to actually make it really viable.
Yeah, and to give a note here, the Renault Zoe, they had some demonstrations using AC charging and an ISO 15118 protocol versus most of the other bidirectional implementations are using a CHAdeMO and DC.
Correct.
If we are, so one of the issues is that there's a lot of cars that cannot do bidirectional charging. So what would be needed to get a car to start participating in bidirectional charging?
Now comes a little provocation. I did that at the end seminar for Parker as well. Basically, I took a car from that was like nearly 100 years old and claimed it to be vehicle to grid ready. Basically, if you can have a connection to the battery, you can do vehicle to grid. So any car that can do DC charging can do vehicle to grid on a DC basis. So I can't really see a lot of cars that cannot do it. I'm perfectly aware that right now it will only be cars that has the newest version of CHAdeMO protocol built in. But in time, let's assume that the 15118, the combo, etc., will facilitate with no problems vehicle to grid. I can't see why all cars shouldn't be vehicle to grid capable just in a few years' time.
So to understand, the limiting factor right now is communication protocol. So as long as the car can speak ISO 15118, it is very likely able to do V2G.
I would say yes.
Okay, great, thank you. Okay, a couple of more questions. You talked about informational and control objects, and you talked about cybersecurity. Are you aware of any work going on to encrypt some of this data?
Oh, there is a lot of work, and a lot of work I'm not really familiar with. I'm not really that much into cybersecurity. My version of cybersecurity is really this, more like only one should have a control at the same time. The rest of the cybersecurity, meaning encrypting data, I'm not really familiar with that.
Okay. Some of the work you've done in DTU is looking at the impact on health of the batteries from V2G. Are you able to comment on that?
Sure. I mean, again, we did some measurements on these cars from Frederiksberg Forsyning and quite a few more. We've also been talking together with Nissan regarding models and modeling of all of these items. And so far, it seems like there's not a lot of wear and tear on the battery using vehicle to grid. On the Frederiksberg Forsyning, we see something that's roughly down where it becomes not really measurable. We are talking a few percent over a few years. So to be quite frank, doesn't look like it's doing a lot of impact on the battery. We're talking about cycle wear of a few percent. We're talking about the worst version of vehicle to grid we can imagine. That's frequency control all the time. And still we are not seeing a huge impact on the grid. Oh, sorry, the battery.
Okay, thank you. I encourage participants, if they have any questions, please do put them in the chat box. Alternatively, if you raise your hand, you're able to speak. Continuing on the degradation, are you able to share what information do we need to collect to help us test if there was an impact on degradation? Considering that usually information around batteries are commercially sensitive and it is hard to get it unless you're reverse engineering and getting this information from the canvas, for example.
I agree. I mean, normally you would consider the state of SOH, the state of health, to be the measurement you would have. That's basically the degradation in capacity. But still, also, since this is kind of hidden on the canvas, it's not really available. It's not really meant to be available. And you can't 100% trust what you find on the canvas because we don't really know what's the sort of, how is it measured, how is it calculated. But to sort of spin a little bit of a tail on this, how you measure it, we've done quite a lot of measurements over quite a few years. And basically what we do is discharge the car and see how much energy we can fill back in. And this is, again, a little bit unsecure because all of this is really controlled by the car itself using the BMS. We can't override the BMS. And we've also discussed this with different kind of producers of both cars and BMS systems. And it is an issue. I mean, a battery is not a fixed item like a tank. It does not have a fixed capacity. It depends on temperature, various other variables. So we are really trying to make something fixed, get a certain number on something that's kind of variable. And it's not a simple task. We try to do like test the cars on Frederiksberg at least once a year, probably twice a year, under pretty much the same conditions. Means we get them to our lab, the same temperature, we discharge them, we charge them up again, and then we kind of have a very good idea. But if the BMS chooses in the middle of our test to do some cell balancing to cool or heat the battery, then it will interrupt with our measurements. So it's not a simple task.
Thank you. We got something maybe related. So you talked about impact on battery degradation. What about the impact on the power electronics?
Regarding lifetime, you mean?
Yeah, any impact if you're doing a lot of services to the grid, does that impact the power electronics?
Well, it's a good question. I mean, you would normally have wear and tear on this. I don't think we've made any measurements on how much it would do. To be quite frank, we haven't had any power electronics that really failed. So far it looks good. But to be quite honest, we haven't looked into this in regards with the EVs.
Great, okay. Last question. You've provided a lot of information. Where can people find more?
Yeah, first, I do know it was a lot of information. And as I said in the start, it was, I think I showed 16 projects. And I think we have at least double of that running right now. So you would have to go to the project homepage. Normally you could Google it from the name and add DTU or something like that. If that's not sufficient, you can contact me, Peter Bach-Andersen, as you mentioned before, or this head of the group that I showed on one of the slides, Christian Traffert.
Great, thank you so much, Thomas. Anything you'd like to summarize? Do you want to have an end note of what do you think we should do? Maybe this is summarizing again everything you said. How do we future-proof a charging station to ensure a proper integration with the electric vehicle, with the grid?
I would actually come with a little bit of not a recommendation, but ask the people out there to make more use cases, more examples, more demonstration projects, and then share this with the standardization groups, because that's really what sort of will bring this transformation to an end. That is, if we have sufficient use cases, then they can make the standards that we are wanting right now.
Excellent. Thank you so much, Thomas, and thank you for the participants.
Thank you.